Alright, equivalences. These are very useful and helpful things. They can simplify like really complex ideas because it allows us to represent things in a different way. And we've come across equivalences many times in previous videos, but now we want to introduce more examples to just help solidify the understanding. Now, I'm going to give you an example of an equivalence, and this will be really useful. It comes up a lot, and you can just automatically use it whenever you can apply it, basically. So this equivalence, basically what we have is, if we have two symbols or two statements that are connected together with an AND statement like this, then this is just equivalent to saying not P or Q, or not Q, sorry. So what happened here? Well, you can just think of it as distributing the negative signs inwards, and also what happens is this AND sign over here, it flips to an OR sign right there. So if you just perform these steps, namely distribution of the negative sign and changing the AND operator or AND statement into an OR statement, then you'll end up with an equivalent statement. And it turns out that this works the other way around as well. In other words, if you have an OR statement instead of an AND statement, then you can essentially do the same thing. You distribute the negative signs inside, and you flip the OR into an AND this time. So you have not P, this time it's an AND, not Q. So yeah, all you have to do, distribute the negative sign, and whatever's connecting P and Q together, you just have to flip that around, and you'll always end up with an equivalent statement. And this is something that can be easily proven with a truth table. You just have to show that the columns of these two guys are equivalent to one another, and you just do that one by one. You just make one table for this guy, one table for that guy, or you can put everything in a really big table if you have to. And I'm not going to do that because I assume that by this point you are already knowledgeable enough to construct a truth table by yourself, so you can actually prove it by yourself this time, and I think that it would make a good exercise to do that. And besides, it's not difficult at all, actually. So there's more equivalences to talk about, and this one has to do with what we learned in the previous video, which was about quantifiers. So quantifiers, you have this guy and this guy, and just as a recap, you can attach these two statements like that, and it basically allows you to communicate more complex ideas about the statement that you're dealing with. So this one means that for all mathematical objects X, they have to satisfy Px, whatever the statement Px is supposed to mean, or whatever meaning you assign to it. Now this one means that there exists at least one mathematical object which satisfies Px, whatever meaning you assign Px with. And so you have these two different ways of communicating or expressing your ideas on the statement Px, whether or not all mathematical objects satisfy Px, or whether or not there just has to exist at least one mathematical object which satisfy Px. Now it's just natural to ask if there's any connection between these two guys. In other words, is there any equivalence relationship that we can use to move from one quantifier to another quantifier, just so that we can express ideas in a different way or with different symbols whenever it is appropriate to, or whenever it is necessary to use a different symbol. So this is a quite useful thing to know, because sometimes you want to be working with, let's say, this statement instead. So now you do have a tool that allows you to convert this statement from this form, or using this quantifier, into something that uses this quantifier instead. And maybe that helps with the problem that you're working with. And who knows, okay? So it might be useful, and we're gonna see if that helps in later videos or not. Alright, so what equivalence relationship can we extract out of this? Well, let's start with an English sentence, okay? Let's say nobody is perfect. Alright, so that's the English sentence, and let's try to communicate this idea through logical symbols and statements. So how can we communicate this idea? Well, we can say that there does not exist a person X such that they are perfect, right? So let's just repeat that again. There does not exist, well, usually X stands for a mathematical object, but right now the question that we're dealing with is not mathematical in nature, and I specifically chose like an English sentence just so that it's easier to understand. So we're dealing with English statement now, and the word nobody in particular implies that we are dealing with people here. So X is not the mathematical object, but rather X is now talking about, well, people. So there does not exist a person which satisfies being perfect. Alright, so that's one way of interpreting things. But on the other hand, we have a different way of doing so. We can say that all people X satisfy not being perfect, right? All people X satisfy not being perfect, therefore nobody is perfect. And you can quite easily see that both of these communicate the same idea. There does not exist a person that is perfect, and all people are not perfect. And those two sentences, number one and number two, they're just rephrasings of this sentence, nobody's perfect. Therefore, they have to be equivalent to one another because they, in the end, they're just communicating the same idea all throughout, just in a different way. And there we have it. This is the connection between this quantifier and this quantifier. And this allows us to switch between quantifiers whenever it is necessary to do so. Alright, so what happened here? Well, all you did is you moved the negative sign behind the quantifier, and when the negative sign jumps into this spot over here, it converts the E to an A. So you move the negative sign backward and you change the quantifier. And when you do that, you're going to end up with a statement which is equivalent. And well, it turns out this works the other way around as well. So this time we're not using this quantifier. Let's use this quantifier instead. And we'll also show that this works as well. In other words, the not sign can just jump back and the A can convert to an E, just like this. And therefore, oops, why did I erase that? Okay, and therefore, this is equivalent to that by the same rules over here. Except we haven't really proved it yet. We just used our intuition. Well, if it works here, if the jumping thing works here, then it should work for this guy as well. But we haven't really proved it yet. It's just all intuition. So we have proof statement number one, and all that's left to do is proof statement number two. And to prove statement number two, what you can do is you can just do the same thing. You can create an English sentence and show that it can be communicated in this way and also in this way. Now you can do that to show that these two are equivalent to one another, but let's use an even more cool way, okay? Let's start with this guy over here. So we have EX not PX, and well, that's just equivalent to not EX not PX. And that's because the two not signs can just cancel each other out. This is something that we've dealt with many times in previous videos. And now we can use statement number one. Statement number one is already proven. So what we can do is we can move the negative sign backwards, and then the E can convert to an A. So that's exactly what we will do. The negative sign over here moves backwards, and the E converts to an A. So now we have two negative signs in front of the px now. And remember, two negative signs just means that we can cancel it out together. So in other words, we just have px by itself. And there we have it. The thing on the right side over here is equivalent to the thing on the left side. Therefore, we have proven statement number 2. No need to construct English sentences again. And I should note that the choice of the English sentence does not matter. In other words, the meaning that we assigned doesn't matter. And it always doesn't matter, like I said. And like I said, and I repeat it many times, whatever meaning you assign to a statement shouldn't matter at all, because it's not going to affect the way that you're going to construct a truth table. It's not going to affect the relationship between the symbols at all. So I could have just used a different sentence. Let's say instead of nobody is perfect, I could have said all unicorns are purple, which is like a completely random thing. And you would still end up with the same equivalences. So let's now use all that we have learned in an example. Let's say we have the sentence, everyone has a friend they do not like. And we want to take the reverse of this statement. So what if I reverse this statement over here? What does that mean? How can we communicate that in the English language? Well, let's just, for a start, turn this thing into symbols. Let's express that idea in terms of symbols. So what do we have? Well, for all people X, then there exists a person Y such that, and I'm going to introduce a symbol F here, and I'm going to say that it means X and Y are friends. So if I put X and Y here, this means that both X and Y are friends. And I'm going to attach an AND symbol there. So X and Y are friends, and X does not like Y. So like this. We're going to use the L symbol to represent like. So if I attach a not in front of it, this means not like. So what do we have all together? For all people X, there exists another person Y, such that X and Y are friends, and X does not like Y. So this is exactly what we have on the top over here, and we just translated that in terms of logic and symbols. Now, let's just remove the bracket, because honestly that just doesn't matter. And what we can do right now is we can apply our equivalences that we have learned so far. So what's one equivalence that we have learned? Well, we can move this backwards, right? And when the negative sign jumps, the quantifier changes. So this just changes to an E. So we have E of X, and then we have a not sign. The not sign jumped. Now, what can we do? Well, we can make the not sign jump again, right? And once we do that, the E converts to an A. So we have an A and Y, and the not sign move behind. Alright, so what does this look like? Well, this looks like what we did in the first part of the video. We just distributed the negative signs. And what do we have? Well, remember, distribute negative sign means that we have to change the operator. So we just have to flip it around. If this is AND, then we just have to change it to an OR. Now, the negative sign distributes here. So there's two negative signs, and that just cancels out. So we can just say that there's no negative signs there at all. And over here, a single negative sign gets distributed to the F. So let's just change the F. So the F is just given a single negative sign. Like that. Okay. So, one more equivalence, just to simplify everything up even further. And this is an equivalence that we learned in the if-then statement. Namely, if we have a statement P and Q, so if P then Q is equivalent to not P or Q. And we proved this in a video titled If-Then Statements. I can't remember if it's part 1 or part 2. So if you want to understand the concept and the idea behind this equivalence, then just head over to that video. Well, this has an awfully similar structure to this guy, right? So that means we can just convert that to this over here. So this just means that what we have overall is fxy arrow lxy. And that's just it. The statement at the top here is equivalent to the statement at the bottom over here. So if everyone has a friend they do not like, and we reverse that, this is the same as saying that there exists a person X such that for all people Y, if they're both friends, then they both like each other. So this over here is true and this over here is true. They just essentially communicate the same idea. You just have to think about these two different representations a bit, and you'll be convinced that both of these guys are equal. So this is just a deep dive into more complicated equivalences. And yeah, stay tuned for the next video.